Okay, it is 9 p.m. on a Friday night. It's 9:30 p.m. You know where your math teacher is. Folks, I want to do a couple more, or maybe two more examples from section 4.1, but I wanted them to be separate from the lecture. Not because they're not important, but the lecture is getting a little bit long. And these are the more challenging examples, so I want you to be able to look at them specifically if you need to. So here we're given the function f of t is equal to t plus the cotangent of t over 2, and we're given an interval for which we want to find the absolute extremum. So remember our steps. Step 1, find the critical numbers. Okay, so to find the critical numbers, we need to find the derivative of the function, which would be 1 minus cosecant squared of t over 2 times 1/2. Why is that 1/2 there? Well, that 1/2 is there from the chain rule. Okay, so now we want to know where is f prime undefined, and where is f prime equal to 0. So let's find out. To figure out where it's undefined, that's kind of a complicated question. I think we can handle it. The only operation that we're doing there that can get us into trouble is taking the cosecant of a value. And remember, we cannot take the cosecant of which values? Well, let's look at the graph real quick to make sure we can remember. So I remember that the cosecant function has asymptotes at your multiples of pi. And the graph of the cosecant function looks something like this. Remember, that's at -1, and that's at 1, and I'm sorry, folks, it's a horrible lie. Yes, it is 9 p.m. Okay. So let's put one more asymptote in there, just so. Okay. So, and where does it have these local maximums and minimums? They occur at the multiples of pi over 2. So it's pi over 2. And this is at pi over 2, and this is at 3 pi over 2. Okay. So that's our cosecant curve. So it's undefined at multiples of pi. So what we don't want is we do not want t over 2 to equal a multiple of pi, which means let's maybe put a slash on there. We don't want t over 2 to equal a multiple of pi, because if it did, then it would be undefined there. So that means we do not want t to equal a multiple of what? Well, if we multiply that 2 over, then we don't want t to equal a multiple of 2 pi. But if we look at where our function, where we're talking about our function, we're somewhere in between 0 and 2 pi for t, so we're okay there. Okay? So let's just say that f prime is defined everywhere on the interval pi over 4 to 7 pi over 4. Great. So then we want to ask, well, where is f prime of t equal to 0? So we set f prime of t equal to 0. That happens when 1 minus the cosecant squared of t over 2 times 1/2 is equal to 0. That happens when, subtracting that over, 1 is equal to the cosecant squared of t over 2 over 2, taking that 1/2 into the denominator. But then let's immediately multiply that 2 over to the other side. So if I multiply both sides of that equation by 2, I get 2 is equal to the cosecant squared of t over 2, which tells us that plus or minus the square root of 2 needs to equal the cosecant of t over 2. Whew. This is a long question for just finding the critical numbers. Okay, well, I have a hard time working with cosecant, so I'd like to convert this to a sign question. So that means that we want to know where is 1 over plus or minus the square root of 2 equal to the sine of t over 2. Okay, so what did I do here, folks? Let me do that a little more slowly. So I could say that's plus or minus the square root of 2. I want that to equal 1 over the sine of t over 2. And then let's go ahead and invert both sides of this equation. So then we get 1 over the square root of 2 with plus or minus. We want that to equal the sine of t over 2. Okay. Well, when does that happen? That would happen if t over 2 was a multiple of, an odd multiple of pi over 4, right? So, for example, that would happen if t over 2 were equal to, let's just put a few up here, minus pi over 4, or pi over 4, or 3 pi over 4, or 5 pi over 4, etc. Okay. There's more, but I think this will be enough to encapsulate what we want. So that would happen if t were equal to minus pi over 2, or if t were equal to pi over 2, or if t were equal to 6 pi over 4, holy smokes, 6 pi over 4, 2 is both of those, so that'd be 3 pi over 2, and 10 pi over 4, which would be 5 pi over 2. Okay. Maybe I could have seen the pattern as I was doing that. Anyway, of those values, and I could have listed others, and there's actually a much more methodical way to arrive at this answer, but of those which are in the interval from pi over 4 to 7 pi over 4, well, only these two are. So those are my two places where the derivative is 0. Okay. So our only critical numbers are where t is equal to pi over 2, or where t is equal to 3 pi over 2. Okay? These were critical numbers because this is where f prime of t was equal to 0. And notice that there were no points where f prime of t was undefined. Great. Okay. So now we found our critical numbers. What do we want to do? Well, we want to go ahead and evaluate both our critical numbers and any endpoints into the function itself. So just because I'm running out of room here, f of t, let's see, we said that was t plus the cotangent of t over 2. Let me double check that. Awesome. Okay. And our critical numbers that we want to evaluate this function at are at pi over 2 and 3 pi over 2. So we're going to evaluate this function at pi over 2. We're going to evaluate this function at 3 pi over 2. But we're also going to evaluate it where? Well, where could we have extrema? We could either have extrema on the interior, where we have critical numbers, or on the endpoints, and so we need to also check those. We need to check f of pi over 4 and f of 7 pi over 4. Okay. So let's see what we get here. If I plug in pi over 2 into the function, I get pi over 2 plus, let's see, this would be the cotangent of pi over 4. Okay. Oh, I guess it's going. Pardon me, folks, I had to calculate a couple of the endpoints here. So let's see. This would be, oh, we're back to, well, shucks. Let me just pause. Okay, resuming here. Okay, so the pi over 2, and then what is the cotangent of pi over 4? Well, remember the cotangent is the cotangent is the cosine over the sine, and so it's radical 2 over 2 over radical 2 over 2, which is equal to 1. Okay? And if we plug in 3 pi over 2, we would have 3 pi over 2. Remember, I'm plugging this into the original function. This is the cotangent of 3 pi over 4. Well, that's equal to 3 pi over 2 minus 1. And if I plug in the endpoints here, then I've got pi over 4 plus the cotangent of, careful, pi over 8. And this would be 7 pi over 4 plus the cotangent of 7 pi over 8. Okay, and I've got these in Wolfram alpha here. Let's pull them up. Let's see. So that last one evaluates to approximately 3.08. Approximate symbol, 3.08. And the second to last one, that evaluates to approximately 3.12. So it's approximately 3.12, and I didn't look these up. Pause the video while I do so. So I looked those up. Let's see, we have 3 pi over 2 minus 1 is approximately 3.71. So this is approximately 3.71. And when I plugged in the other value, so if we look at pi over 2 plus 1, we get approximately 2.57. Okay, so that was kind of a lot of work, but we were looking for our global extremum. We said that the global extreme could either occur at the critical numbers, which were at pi over 2 or 3 pi over 2, or the global extremum could occur at the two endpoints. So we checked each of these in the function, and then we simply look for which one is the greatest and which one is the least. So the extremum, the global maximum, occurs here. Okay? So that means we have a global max at 3 pi over 2 of, okay? And although I used a decimal approximation for comparison's sake, because I'm not so good with some of these fractions, let's go ahead and list it as a y value, 3 pi over 2 minus 1. That is the global maximum value. And then we have a global min where? Well, which of these values is the smallest? It is right here. So we have a global min at, and again, let's give the exact value, pi over 2 of pi over 2 minus 1. Okay. So on the graph here, which depending on when you printed out the assignment, you may not have, on the graph here, let's just go ahead and label the points that we have. This was our, these were our two endpoints, which I've labeled with the dots here. Maybe not the best choice of colors. And then these were our two extremum. We had one right here at pi over 2. So again, that's the ordered pair, pi over 2, comma, pi over 2 minus 1. Folks, that's a mistake. I'm not going to fix it. That's a plus 1 there. And this was 3 pi over 2, comma, 3 pi over 2 minus 1. Notice those were the two extremum. In this case, the endpoints weren't the extremum, but that is not necessarily always going to be true. You have to check your endpoints on these problems. So please do not forget, you have to check your endpoints. Okay, what else do I want to say? Well, besides graphing, so in red here, you can see I've graphed the that particular t plus the cotangent of t over 2. But then I also went ahead and graphed the derivative here. The derivative looked like this. That was the derivative of this function. And just as a reminder then, when we were looking for global maxes and mins, we looked for where the derivative was 0. Well, that happened there at pi over 2, and it happened again here at 3 pi over 2. So these were, because that's where the derivative was 0, those were our two candidates from the interior of the domain where we were looking for our global extremum. But this use of the derivative to find candidates for where we might have global maxes and mins doesn't pick up what's happening at the endpoints. So we had to separately check the two endpoints. I hope this was helpful. Thanks for watching.